Today, we're going to decode a language that is literally all around us. It's a language that governs everything, from the planets up in the sky to the tiniest atoms in our own bodies. We're talking about the universal language of motion. So, what do a pendulum, a planet, and a guitar string all have in common? I know, it sounds like the start of a bad joke, right? But the answer is they all speak the same physical language. They all follow these fundamental rules of motion, a set of principles that describes and predicts how pretty much everything in the universe moves.
Okay, let's just dive right in. Here's our game plan. We're going to start with the absolute basics, then we'll check out the different types of movement, learn how to measure them, uncover a really special rhythmic pattern, see how to visualize it all, and finally, look at how this stuff actually impacts our world.
First things first, before we can even talk about fast or slow or straight versus circular, we have to agree on what it even means for something to be in motion. It seems obvious, but, there's a really key idea we have to get our heads around. So here's the crucial point. Motion is always relative. A book sitting on your table is totally at rest, relative to you. But think about it. Relative to the sun, you, your table, and that book are all hurtling through space at an incredible speed. So motion is always described with respect to a frame of reference. All right, so now that we know motion is relative, let's look at the different paths it can take. See, motion isn't just one single thing. We can actually classify it into a few key categories. It's like building a catalog of movement. The most straightforward type, pun intended, is rectilinear motion. It's really just a fancy term for moving in a perfectly straight line, like a train on a straight track or an apple falling directly from a tree. Simple as that. And then, of course, we have circular motion. This is the path of a planet going around its star, a car on a roundabout, or even just the tip of a clock's hand. The whole time, the object is constantly changing its direction to stay on that circular path. And this brings us to something really cool, periodic motion. This is any kind of movement that repeats itself over and over again in a predictable cycle. Think about a swinging pendulum, the Earth's orbit around the sun, or even the beating of a heart. It's got a rhythm, a regular interval, that we call its period. Okay, to truly speak the language of motion, we need more than just categories. We need a way to measure and describe it precisely. We need its grammar. So let's look at the key metrics we use to do just that. First up, let's get this straight. Imagine you walk 10 meters north, and then you turn around and walk 5 meters south. The total distance you traveled is 15 meters, right? But your displacement, how far you actually are from your starting point, is only 5 meters north. Distance is the whole journey. Displacement is just the straight line from start to finish. Now, speed is the one we're all familiar with. It just tells us how fast an object is covering distance. And we calculate it with that classic formula we all learned in school. Just divide the distance you traveled by the time it took. Now, here's a critical difference that you might not think about every day. Speed versus velocity. Speed is simple. It tells you how fast. It's what we call a scalar quantity, just a number. But velocity is a vector. It tells you how fast and in what direction. So 50 kilometers per hour is a speed, but 50 kilometers per hour north, that's a velocity. This means two cars can have the exact same speed, but totally different velocities if they're not going in the same direction. And this one is a big one. Acceleration is not just speeding up. Since it's a change in velocity, you are accelerating if you speed up, if you slow down, or if you simply turn a corner. Why? Because turning changes your direction, and that changes your velocity. Okay, let's go back to that idea of periodic motion for a second and explore one of the most important patterns in all of physics. It's a special kind of rhythm that we call oscillation. So this is a specific type of periodic motion, just a back and forth wiggle around a central point. And it is everywhere, from the vibrating strings of a guitar that create sound, all the way to the oscillation of atoms that we actually perceive as temperature. The ideal, purest form of this is called simple harmonic motion, or SHM. The best way to think of it is like stretching a rubber band. The farther you pull it away from its resting point, the stronger it tries to snap back, right? In SHM, that restoring force is always trying to pull it back to the middle. And this pure rhythm has this fascinating, kind of hidden connection to another type of movement we've already seen. And this quote just reveals the whole secret. Picture this. You've got a ball moving in a perfect circle at a constant speed. Now, imagine a light shining on it from the side, casting a shadow on a wall behind it.
That shadow, moving back and forth on the wall, is in perfect, simple harmonic motion. It's just an amazing, beautiful link between two types of movement that seem totally different.
Numbers and formulas are great, but sometimes the best way to really understand a journey is to just see a map of it. And that's where graphs come in. They give us this powerful visual story of an object's motion. On a distance time graph, you've got time taking along the bottom axis, and the distance from the starting point is up the vertical axis. The steepness, or what we call the slope of the line, tells you the speed. So a really steep line means a high speed, while a completely flat horizontal line means the object has stopped. Time is passing, but its distance isn't changing at all. So if an object is moving at a nice, steady speed, we call that uniform motion, and it shows up as a perfectly straight sloped line. But if that line starts to curve upwards, the object is speeding up. If it curves and starts to flatten out, it's slowing down. The shape of that curve literally tells the story of its acceleration. Okay, so why does any of this matter? What's the big deal? Well, because understanding these principles is the absolute key to engineering our modern world and explaining some truly powerful, mind-blowing phenomena. When we combine this idea of oscillation with some kind of driving force, we get a powerful effect called resonance. And you have absolutely experienced this. If you want to get a swing to go really high, you don't just shove it randomly, right? You push it at just the right moment in its arc. That is resonance. Every object has a natural frequency it likes to vibrate at. And if you push it at exactly that frequency, even tiny pushes can build up to create massive oscillations. But this effect can also be unbelievably destructive. The famous collapse of the Tacoma Narrows Bridge was caused by nothing more than the wind providing a steady, pulsing force that just happened to match the bridge's natural frequency. And this amplified its oscillations until the entire structure literally tore itself apart. And this brings us to a final thought. From the atoms that make you up, to the buildings you live in, to the music you listen to, everything has a natural rhythm. Motion isn't just about getting from point A to point B, it's about the vibrations and frequencies that define our universe. So maybe consider the unseen vibrations that are shaping your world. What happens when we learn to sync up with them?